everyone to our session for physical sciences. My name is Temba. Today we are focusing our attention on electrical power. So the term power has got many different meanings in different contexts. Now the context for today, which we want to explore, has a lot to do with electric circuits, because power has many real life applications. But when we look at circuits and we talk about power, what is it that we are actually referring to? This is what we want to establish, okay? So without any waste of time, let's look at the flow chart, which actually outlines, the related concepts, in terms of the mind map, okay? Right, so what is it that we already know? We know something about current, okay, which is the rate of flow of charge, as well as potential difference, which we some alternatively refer to as voltage, which is actually the work done, okay, per coulomb of charge, or energy that is supplied per coulomb of charge by a source. So current is actually I is equals to Q over delta T, okay, right? While voltage is actually about W, which is energy per coulomb of charge, okay? We know also that resistance involves the ratio of voltage and current, okay? We also have managed to actually look at the Ohm's law, which talks about the mathematical relationship that exists between current and voltage at constant temperature. And we are familiar that some conductors are actually ohmic in the sense that they obey Ohm's law, while those that do not obey Ohm's law, we've described them in terms of non-ohmic. We also know that there are two types of circuits, which is parallel as well as series. But what stands out about these two types of circuit is that the current and voltage is something that we need to really understand, that in a parallel circuit, current is divided while voltage remains constant. Well, the opposite is true with the series circuit, okay? So the focus for today is actually on electrical power, right? Okay, now this is the thought for the day, okay? Have you ever thought about the energy conversion, all right, that takes place in an electric circuit? Okay, what is it that we already know? We are familiar with the fact that energy cannot be created or destroyed, but what actually happens to energy is that it's converted or transformed from one form to the other, okay? Now, we need to be very careful. We talk of energy conversion or energy transformation, not energy transfer, because transfer is definitely something else. It means transferring energy from one object to the other. Yet, our focus for today has to do with the conversion of energy from one form to another, okay? So this is the thought about energy conversion that takes place in an electric circuit, okay? And then secondly, how the power of a light bulb affects its brightness. So we're talking about power and brightness. Now, brightness is a qualitative dimension, because we can say it's dim or it's bright, but we can quantify power in terms of how big or small the power of an electrical device is, right? Okay, so these are the keywords that we would focus our attention on, that you need to take note of, and essentially we would use these keywords, once too often than others. So the three keywords that we've identified for the purpose of today's discussion is power, energy, as well as work done. But you'll also realize that these terms are also related to each other, okay? Right, without further ado, let's look at energy transformation that takes place in an electric circuit, okay? What we already know in terms of energy from way back is that energy is the capacity to do work. In other words, work cannot be done without energy. So for work to be done, energy must be converted or transformed from one form to the other. And in that sense, or in a scientific context, we are saying that work is done when energy is converted from one form to the other, okay? And you also need to understand that energy is work and work is energy. Energy is measured in joules, work is measured in joules. Both quantities are actually scalars in the sense that we only talk about their magnitude or their size, okay? So when work is done, when energy is transformed from one form to the other. So transformation is the actual conversion, right? So transformation has to do with conversion of energy, right? Okay. Now, the potential difference, which is the voltage of a battery, is the energy supplied per coulomb of charge. Okay, this is a very important concept that we briefly touched on when we looked at the concept map. Okay, now the role or the function of a battery as a source of energy in an electrical circuit has a lot to do with energy transformation. If you look at a cell or a battery, in its own right, what it does is that it is the source of electrical energy, but that electrical energy comes from chemical potential energy, which is stored inside the battery. So already we are beginning to talk about energy conversion from chemical potential energy inside the battery to electrical energy, where the charges starts to actually move. Okay, so the potential difference or voltage of a battery is the energy supplied per coulomb of charge. We're also familiar with the fact that 1 volt, okay, of potential difference is equals to 1 joule of energy supplied per coulomb of charge. Okay, so as the battery supplies energy, it does work. Well, why do we say it does work? Remember, the main thing about work done by the battery is that it converts chemical potential energy into electrical energy. So that conversion involves work done. So as the battery transforms energy, it does work in the circuit, thereby discharging its role in as far as the electrical circuit is concerned. Right. So as the battery supplied energy, it does work in moving the charges between 2 points. Okay, right? And then a light bulb as an electrical device, and you must also think of a light bulb as a form of a resistor, right? Okay. So a resistor is any electrical component in a circuit that converts electrical energy into other forms. Okay. So a light bulb converts electrical energy into light, but not all of it becomes light. Some of it becomes heat, because as it does its work, as it transforms energy, some of the energy becomes heat. It gets warmer and warmer. Okay, so this is just an example. You think of a heater, a heater as an electrical device. What does it do? It transforms or converts electrical energy into heat. Okay, a speaker, what does it do? It transforms electrical energy into sound energy. So there is a lot of energy transformation that takes place in any or in a typical electrical circuit, right? Okay. Now, what about the work done by the light bulb? So as the light bulb does work, okay, it transforms energy, okay, or it converts energy from one form to the other, and we've identified that work is done when there's a change in energy. So work is energy, energy is work, because the work of the light bulb cannot be done without the energy conversion. So take note, work is symbol W, and the W is actually a capital letter, okay? The SI unit is the joule, okay? And we've said 1 joule of work is done when, 1 joule of electrical energy, for example, in a light bulb, is converted to light energy, okay? So a joule of work done by the light bulb when a joule of electrical energy is converted. So we're saying work is done when energy is converted, so from one form to the other. That's the main idea, all right? Okay, now let's talk about power, because this is our key focus for today, okay? By definition, power is the rate of electrical conversion in a circuit. Rate, that's the key word, and then electrical conversion is another key word. But remember, when it comes to definition, we cannot overemphasize the importance of the examination guidelines. The key words, you need to use them in the correct context, because definitions form a key part of the terminology. It is the language that we speak, and in the context of circuits, we talk about power in terms of rate. The moment we say rate, we are able to then say, okay, there's a component of time that is involved. We use the word rate in many different contexts, but in as far as power, it has to do with how much energy is converted from one form to the other in a given time. And then the SI unit of time is obviously the second. So when we say a unit time, we're talking about a second. All right. So this is the rate of energy conversion in an electrical circuit. Okay. Right. So in terms of the symbol, P is the capital letter once again, because the small letter p represents something else, okay? So take note of that. So this is the concept, okay? Mathematically, that's how we represent the equation. So this is transfer of energy, this is conversion of energy, okay? This is conversion of energy, okay? Which has to do with work done, okay? Is conversion of energy or work done, because work is done when energy is converted from one form to the other. So this is a joule, right? Okay, and then this is the time, and the time is the second. Take note, we use small letter s instead of SEC. So this is not the unit of time. The unit of time is actually the second, okay? So if we talk about a watt of power, let's say a light bulb has a power rating of 1 watt. What does that mean? It means that the light bulb converts 1 joule of electrical energy to light energy for every second, okay? So correspondingly, if we had, let's say for argument's sake, a 20 watt device, what does this mean? It means it converts 20 joules of electrical energy into whatever form for every second. So for every second, it means in 1 second. In other words, we've got 20 joules, okay, in every second. This 20 joules of work done or energy, conversion for every second, okay? That's the main thing. Now, if we are to measure power in an electrical circuit, okay, we know that power is the product of voltage and current in a device, because the context here is that we're talking about power. It's not the mechanical power, but it's electrical power, okay? So the circuit is what is of interest to us. So if you get the product of voltage and current, it actually gives you the power, okay? Because we know that voltage is equals to joule per coulomb, okay? That's a joule per coulomb, okay? This is energy, per coulomb of charge. Current is actually an ampere. An ampere is another coulomb per second, okay? So this is exponent 1. That will take care of itself. Then this gives us a joule per second, which is exactly what a watt is, okay? All right, so an ammeter would measure the current, while the voltmeter will give us an indication of the potential difference. It could be across that light bulb, okay? So if we get the product of the two, we are able to determine the power, right? Okay, now, have you ever thought about the meaning on the labels of light bulb? There are, everyday life observations that we make, and which relates to power in more ways than one. You walk into a room that has got a 60-watt bulb versus a room which has got an 80-watt bulb on, okay? The obvious differences that you'll notice is obviously the brightness, So brightness is qualitative. What do we mean by that? A 40-watt bulb, for example, glows dimmer compared to an 80-watt bulb. So if you compare 40 watt versus 80 watt, 80 is double 40. So even in terms of brightness, which is something that we want to actually verify using some form of a simulation so that we really understand what exactly the power rating is all about. So a bulb can be marked 220 volts, 40 watts. What does this tell us? It tells us that a voltage of 220 volts that is connected to that light bulb will actually actually dissipate 40 joules of energy for every second. So this is what it means. In other words, we're talking about 40 watts and breaking it down. So this is the real life application of it, okay? So we have also spoke about the brightness which has to do with how does it glow dimmer or brighter. So it's a comparison. So the power rating, it's something that we obviously want to understand even deeper. So the comparison between a 40 watt and an 80 watt bulb is basically on the brightness and the power or the amount of energy, conversion for every second. Right. So having said that, let's take a short break. Now, when we come back, we're going to explore even more, circuits with respect to power. Let's take a short breather for now. Welcome back to our second slot. We still are talking electrical power, but now we want to look at the different quantities in terms of voltage, current, and resistance, how exactly they impact the power of an electrical device in a circuit, okay? Now, we understand that for us to measure power in a circuit, we need to have voltage and current, basically. So the voltmeter connected across a component will give us an indication of how much work is done per coulomb of charge across that component, while the ammeter reading gives us the current to say how many coulombs of charge pass through a point per second. So knowing that P is equals to VI, that's the basic, okay? Now we also know that from the Ohm's law, we've got V is equals to I R, okay? So in the event that we don't have, the voltage in a particular circuit, we are able to determine power using P is equals to, so this is our V, okay, just to quickly show you how we arrived at one of the three formulae. It's that P is equals to, where there is V, we've got I, R, so that's our V multiplied by I, okay? So this gives us P is equals to I squared multiplied by R. So we would use this equation to calculate the power of an electrical device if we know how much current passes through that device given its resistance. However, if we have a situation where we do not have the current, and then from the Ohm's law, we know that I is equals to V over R, okay? And then we know that P is equals to VI, okay? Now, if we know that P is equals to VI, then we'll have P is equals to a V, where this I will have I over, we'll have V over R instead, okay? So we'll have V over R, just to correct that, okay? So if we have the voltage, so that's our current, which is V over R, then this gives us P is equals to V squared over R. So these are the three formulae that would use to determine power in an electrical circuit. Now, let's focus our attention on a simulation to look at, a simple example whereby we have a light bulb, and then we're going to vary the voltage from the source, which is the battery, and see how it affects the power, in an electrical circuit, all right? Okay. Now, let's go to the simulation, all right? So here we have a simple circuit. We've got a cell, which is a source. This cell, we will start the voltage with a voltage of 3 volts. It's an open switch, which explains why there's 0 current, okay? And then the resistance of the light bulb shall keep the same at 10 ohms. We just want to see how the power is affected by changing the voltage. We already know that from the Ohm's law, the voltage and current are directly proportional, provided that temperature remains constant. So if we complete the switch, the circuit by closing the switch, there is a reading. So the voltage of the battery is 3 volts, okay, across the 10 ohm resistor. So if we were also to measure the voltage across the light bulb, it will actually give us 3 volts, which is actually the voltage across the source, okay? So all the terminal potential difference is equals to, the EMF of the source, okay? So the 3 volts goes with the current of what? 3 amperes, 0.3 amperes, okay? What if we double the voltage of the source and see how that affects the current voltage, and then would also see the magnitude of, and maybe just get a trend on the magnitude of the power of that is dissipated by the light bulb. So instead of 3, now we double that, it goes to 6 volts, okay? So if it goes to 6 volts, you can immediately see that the current has also increased from 0.3 to 0.6, and that in turn has affected the brightness of the bulb. The bulb is now actually glowing much brighter. So if we measure the voltage across the bulb, it gives us 6 volts, which corresponds to a current of 0.6 amperes. This voltage is the same as that across the what? The source, which is 6 volts, okay? What happens then, I think we'll get the pattern. What happens if we make even voltage bigger, 3 times as bigger as the original one? So this takes us to 9 volts. You can see the brightness is getting higher and higher. And again, the voltage across the light bulb is 9 volts. Current is also increased, okay? Now, let's do the last one, making it 4 times as bigger. So if the voltage that the source supplies is 9, what about if it's 12, okay? Right? The brightness is even increased. The current is increased to 1.2 amperes. So has the voltage across the what? The source, okay, which is 12 volts. Right. Now let's go back to our slide and talk the science behind that. Okay. Okay. Now these are the values that we actually managed to verify. Okay. The voltage across the light bulb was increasing in multiples of 3. Okay. Look at the pattern in terms of the power. Okay. Remember, if voltage increases, so does current. This is based on Ohm's law, which says V is directly proportional to current, provided temperature is constant, right? If temperature remains constant, current and potential difference are actually directly proportional, okay? So it's on that background, okay? Right, now if you look at the resistance of the light bulb, we did not change it. It remained the same. No, the potential difference across the light bulb, when it increases, so does the current, okay? And then the product of, our current and voltage, which is P is equals to VI, that gives us the power, okay? So actually this 0.9, we got it from saying, what's the voltage reading? It was 3 volts, and then the current reading, 0.3 amperes, okay? So this gives us a product of 0.9 watts, okay? That's the power, okay? So this is how we managed to obtain these values. Now, if we look at the trend and pattern, what is very true is that as we increase the voltage, also the current will increase. But how did that affect the brightness of the light bulb? As the current increased, as more and more current moved through the light bulb, there was greater brightness or increased brightness, right? Okay, now from the results we obtained, okay, when resistance remained constant, this is a condition that's very important for us to actually qualify that relationship. Okay, sketch the following graphs: the graph of power versus voltage and the graph of power versus current. But if we are to start with the power versus voltage, you'd realize if we quickly go back to the table of results that we obtained from the simulation, we can see that this is not necessarily a linear relationship. But remember, P is equals to I squared R. At the same time, we're saying P is equals to V squared over R. So if R in both cases is constant, this doesn't give us a linear relationship, okay? So from the graph, we can immediately say, okay, in terms of, so we'll have P on the vertical axis, P in watts, as well as volts, the voltage in volts, okay? That's what it is. And then we get this kind of a relationship, okay? Because we are saying this is based on P is equals to V squared, okay, over R. While the same would happen with the current. Power in watts, okay? And then we've got current in amperes, okay? Again, this is based on the equation P is equals to I squared R, okay? Remember, the resistance was kept constant in both equations. Now, we also get that kind of a relationship between those two. Very, very important, okay? Now, we want to predict a relationship that exists between power and voltage. Let's agree that these are not linear relationships, okay? Okay, what do we mean by that when we're saying they are not linear relationship? Remember, if two quantities are directly proportional to each other, it means if you increase one, the other one will also increase by the same proportion. So you realize that the moment we say current squared, voltage squared, the proportion doesn't remain the same. It becomes, a curve of some sort, which, as we have shown earlier on. Okay, right. Now, that's basically how we actually put an understanding behind the three formulae that we use to determine the power of a device. Okay, now we want to predict what happens to the power dissipated by light bulbs connected in series. Okay, first of all, let's agree that when a circuit is in series, it means all the current passes through that point. Current is constant. Okay. This is what we already know. Current is constant. And then we also know that in a series circuit, voltage is divided. Okay? These are very important facts regarding a series circuit. So in this circuit that we'll use, we'll have a battery of 12 volts, and the assumption is that the battery has negligible resistance. So if the battery has got negligible resistance, what does that mean? It means that the internal resistance of the battery can be ignored. In other words, the EMF, which is the maximum amount of energy that the source can supply per coulomb of charge, is actually equal to the terminal potential difference, right? So in this circuit, we'll have two light bulbs which will serve as resistors, okay? So the other resistor has doubled the resistance of the other, okay? So basically, this is what our circuit would look like, okay? So we just want to compare, what happens in terms of power in that circuit. So let's go to the simulation. Okay, now let's focus our attention on the simulation just to understand what happens in terms of power in a series circuit, right? So if we close the switch, current will start to flow because the circuit is now complete, okay? That's what happens, okay? Now, one of the things that we mentioned, we said the source has a voltage of 12 volts, okay? So that's the energy that it provides per coulomb of charge, while resistor 1, okay, the one that we've highlighted is 10 ohms. Resistor 2 is double that, which is 20 ohms, okay? But we can immediately tell that there is a current in the circuit. The total current in the circuit is 0.4 amperes, all right? So we ask ourselves important questions. How much current passes through resistor 1, which is the 10 ohm light bulb? It will be 0.4 amperes, while the same amount of current actually passes through resistor 2, which is even double the resistance, which is 20 ohms, okay? Now, in terms of brightness, you can tell that these two are quite different, okay? Resistor 2 has got, if we try and look at, the voltage across each one of them. Now, our voltage, in this case, let's measure the voltage across the source, okay? The voltage across the source, we can tell it says it's 12 volts. Now, the 12 volts is split between R1, okay? R1 in this case is 4 volts, okay? So if we say 4 plus the 8, okay, it gives us the 12 volts. This is what we meant when we said that actually voltage is divided, but the current that flows through each of the two resistors is the same. Okay, so in terms of power, which one would dissipate more power? So if we were to determine the power of, that is dissipated by R1, just to compare that so that we can actually understand what is happening there, we would say, okay, so this is our R1, okay? This is our R1, okay? So this is our R1, okay? And then this is our R2, okay? So R1 is actually 10 ohms, okay? While R2 is double that, which is 20 ohms, okay? So P1, which is the power for R1, is equals to the voltage, okay, for 1, which is 4 volts, as it has been measured there, multiplied by the total current, because all the current passes through the 10 ohm, okay? So P1 is actually equals to, what's our V1? It's 4 volts multiplied by 0.4 amperes. So this P1 actually gives us, if we quickly go to our calculator, would get something like 4 multiplied by 0.4, okay? Which gives us what? That value, which is 1.6. So this is 1.6 watts, okay? 1.6 watts. What about for P2? P2 is equals to V2, okay, multiplied by the total current. Why? Because all the current passes through R2. So P2 is equals to, what is our V2? It's going to be 8. The 8 comes from 12 less the 4, okay? Because the total voltage is 12 volts, which can be supplied by the battery, okay? Multiplied by the total current, which is 0.4, right? So P2, that's the power for R2, is equals to, okay, if we go to our calculator, we get something like 8 multiplied by 0.4, okay? This gives us, we get 16 over 5 as a decimal fraction, which is 3.2. Actually, 3.2 is double 1.6 watts, okay? So the power dissipated by a bigger resistor is actually greater if the same current passes through them, okay? Because what's going to distinguish the quantities that are going to be different as far as R1 and R2 is that R1 is half the resistance of R2, while R2 is double the resistance of R1. This is a very important discovery that if you can look at it, guys, it would say to us that we are saying P, okay, P for, okay, P2 is actually equals to 2P1. The condition is that we said P2, okay, R2 is equals to double R1. So if this is a series, current is constant, okay? The only thing then that changed the value of the power is that the resistance is in that proportion. So as a result, we realize that that's why R2 actually glows brighter than R1. What does that mean? It means it converts a lot of electrical energy into light energy per second compared to R1. So that was the main idea, that if the two light bulbs are connected in series, okay, the one that has got a greater resistance, because the same current passes through each one of them, what's going to happen is that the one that has got greater resistance will transform a lot of energy into other forms per unit time, which is the long and short of it. After the short break, we'll use the very same arrangement of resistors, R1 and R2, one becoming double to each other, and see how that affects the power. Let's take a short break for now. Welcome back to our third and final segment. We're still looking at power in circuits. So now we've managed to look at a scenario where we've got two light bulbs. One has got double the resistance of the other, and see how the power actually works out in that circuit. Now let's shift our attention to a parallel circuit, but using the very same measurements for our battery, and the two light bulbs, with one having double the resistance of the other. Okay, so predict what happens to power dissipated by light bulbs connected in parallel. Okay, so in the circuit, we would use a 12-volt battery and then two light bulbs. What this means is that if the resistor 2 or light bulb 2 has got a resistance of X, let's say 10, okay, then resistor 2, if it's 20, it means R1 is going to be 10. In other words, we are saying that R1, the resistance of light bulb 1, is equals to half the resistance of R2. We're still saying the same thing, right? So we'll set up a circuit of this form, okay, and look at the different quantities of electric circuits, which is your current, your voltage, and your resistance as well. But remember, in any parallel circuit, current is actually divided. Like in this case, this is our total current, okay? Because all the current passes through that point, okay? And then this total current is actually equals to current 1 plus current 2. So in this case, what do we have? It's 1,2 amperes plus 0,6, okay? This actually gives us our 1,80 amperes, which is the total current. This is what we mean when we say a parallel circuit is actually a current divider. But we would also verify if indeed voltage remains constant. All right. Okay. Now let's go to our simulation very quickly and look at what exactly that is all about. Okay. Okay. Now, if this is the case, right? Okay. We have got our battery that has got a 12 volt. We've confirmed it's 12 volts. Okay. The resistance for R1 is 10 ohms. If R2 is double R1, it means that it must have 20 ohms, right? It should have 20 ohms, so we've verified that. Okay, so now there is no current flowing in the circuit for one simple reason, that the switch is open. So the circuit is broken or it's incomplete, but the moment we close the switch, this is what happens. Both bulbs, they start to glow, all right? Now, if you look very carefully, the amount of current in the entire circuit is actually 1,8 amperes. So the 1,8 amperes is split between the 10 ohm resistor, which receives 1,2 amperes, while the R2, which has got a 20 ohm resistance, has got half the current. It's very important to also notice that the current that goes through R1 is actually double the current that goes through R2. So R2 has got a higher resistance, which explains why the current is actually lower, okay? So this comes from our understanding of the Ohm's law. But let's verify something regarding the voltage, okay? So what is the voltage across the battery? The voltage across the battery, there it is we've got 12 volts, okay? That's the reading. So if we connect again the voltmeter across the light bulb, we still get 12 volts, okay? Does that mean something? Yes, indeed. It means that even when we connect the voltmeter across R2, we still get 12 volts. So we get a sense that voltage remains constant in this parallel circuit. The only thing that is split is the current, and the current in this case is split proportionally. The one that has got a higher resistance gets less current, which in this case is the 20 ohm resistor. That's got what? 0.6 amperes, right? So this is basically, but if you look at the brightness of these two, we can tell, okay, yes, there is more current for, resistor 1, okay? That's why it glows brighter than resistor 2 for the same voltage. Now, if we go back to our slide, we can say, okay, let's determine the power across or dissipated by R1. So this is our R1, okay? And then this is our R2. Remember, R1 is equals to 10 ohms, okay? While R2 is equals to 20 ohms. This is what we meant when we say R1 is half R2 or R2 is double R1, okay? So we are saying that R2 is equals to 2 times R1, okay? That's the proportion in terms of the ratio, right? Now, if we are to determine the power for R1, okay, we know that for R1, we have both voltage, resistance, we also have current, okay? So we can use any of the three power formulae to determine the power dissipated by light bulb 1, okay? We can use, for argument's sake, V I, okay, which is in this case, our voltage is the same for both, which is 12, okay? And then the current that goes through R1, as you can see from the reading, it's 1,2 amperes, okay? So power for R1, okay, P for R1 is equals to, let's go to our calculator, right? Okay, so from our calculator, we've got 12, okay, 12 multiplied by 1,2, right? This gives us 14,4, right? So this is 14,4 watts, okay? Now let's determine the power that is dissipated by R2. So P for R2 is actually equals to, we have the voltage, which is constant, which is 12, okay? Multiplied by the current, which is 0,6. You'd realize that the current that goes through R2 is actually half that of R1. So P R2 is equals to, if we go to our calculator once more, okay, so we've got 12 multiplied by 0,6, okay? That gives us a power of 7,2, right? 7, okay, 2, right? This gives us 7,2 watts. Now you realize that from the observation that this is actually double that. So the resistor that has got more current, even if we use the formula P is equals to I squared R, it will almost take us to the same thing, because the current is different and also the resistance are different. It means P1 is actually greater or double that of R2. So as a result, that's why bulb 1 appears to be glowing brighter than bulb 2. What that simply means is that the R1 is actually converting a lot of electrical energy to light per second compared to R2, which is why P R1 is equals to 2 times the power dissipated by resistor 2. Okay, so this is the conclusion that we are able to arrive at. Okay, so this is very clear even in terms of brightness. That's why R1 is much brighter than R2. Okay, okay. Now in summary, we understand that power is the rate of electrical energy conversion in a circuit. And when we talk about rate, we're talking about time. So we can think of power in terms of P is equals to delta E, okay, change in energy per unit time, because this has to do with work done, okay? That's our work done, right? And once again, the power rating of a device is actually an indication of how much energy is transformed per second. Okay, let's break this down. If we talk about energy transformation per unit time, a unit of time is a second. And how long is that? It's exactly 1 second. So if you have a power rating, let's say of 7,2 watts, like we saw with R2 in our previous example, what that simply means is that in a second, that light bulb converts 7,2 joules of electrical energy into light, and maybe some of it heat for every second. So that's the long and short of it. Very, very important, okay? Which takes us to the next point, which says a watt of power is 1 joule of electrical energy converted per second. So mathematically, we are still saying 1 watt of electrical power is equals to 1 joule of electrical energy converted for every second. So that's the main idea. Now, let's go back to our equations that we used. We understand that for us to measure power, practically in a circuit, we need a voltmeter reading across a component, as well as an indication of how much current actually passes through that device for every second, or in terms of charge, right? Now, P is equals to VI. We can only use this formula to determine the power dissipated by, you know, a component or a resistor in a circuit, if we know the voltage across it as well as the current that passes through that particular component. And then the second one, P is equals to I squared R. You know, you'd realize that the first equation, there has no V. It does not involve, the second equation does not involve V. The assumption here is that V is actually constant, all right? Okay, so the three formulae will be provided in the data sheet, okay? So the formula sheet actually gives us a whole list of formulae which we need not to cram, but we need to understand. So given a scenario, we must be in a position to identify, one, the correct formula, okay? Make sure that the units are in the correct SI, okay? If there are necessary conversions, you do carry those out before you actually do the substitution. So if a question has got 3 marks, what do? You identify the correct formula, do the substitution, and then give the answer, which should include the correct SI unit. Okay, so in this case, P is equals to I squared R. It says to us, V will be constant. So either the power rating will depend on the current or the resistance. In this case, when we sometimes would write this or represent it in terms of P is equals to V squared over R. It doesn't matter which formula you use, it will definitely give you one and the same thing, all right? So it will depend what quantities you are given. So you must collect the data, and then in this one does not involve current. We would assume that the current is the same, you know, it doesn't change. So for you to identify the correct or the relevant formula, refer to the data sheet, make sure that you copy the formula as it is. Now, speaking of copying the formula, it's not always that will be required to calculate the power. You know, in some cases, you may be given the power and be looking for something else. That something else could be energy, could be work done, it could be current, it could be the resistance, it could be, you know, the voltage or the potential difference. So it's very important that you copy the formula as it is given. Subsequent to that, you do the necessary substitution, and then only one of the quantities in the relevant equation that you'd have identified would be the unknown, and then you can isolate the unknown after the substitution has been carried out. I hope that makes a lot of sense, right? Okay, so in a nutshell, this is what we managed to look into today. We managed to look at power of electrical devices in series and parallel circuits, okay? And understand also that the Ohm's law plays a pivotal role in as far as power is concerned, because we know parallel circuits are current dividers, while these series circuits are potential dividers, okay? So that's very, very important. And then, you know, you must also think about the cost of electricity as one of the real-life applications of understanding what power involves. You'd understand that some devices, you know, they convert a lot of energy, you know, per second. You know, these are heating devices that have got, you know, elements. It could be your geyser, you know, it could be your heaters. But the energy consumption would entirely depend on the amount of energy that device actually converts for every unit of time. Having said that, let's hope it makes a lot of sense. So these concepts start to come together from the Ohm's law to understanding the power, which is basically what we were doing today. We certainly hope that these discussions, they actually help us to, you know, simplify things even much better. So for myself, Themba Ncube, cheers and bye-bye for now.